One of the biggest misconceptions of electrical safety is that it takes high voltage to kill you. The reality is that it is current, not voltage, that causes electrical shock. Electric shock occurs when current flows through your body. Studies have shown that 1 milliamp of current, under worst-case conditions of resistance, can cause electrical shock. System voltages as low as 30 volts AC can supply enough current to shock or possibly even kill.
An easy way to understand electricity is to think of it like water flowing through a pipe. In order to have a flow of water, three things must occur. First, there must be a source of water, like a reservoir. Second, the water must be transported on or in something, like a pipe. Third, there must be a source of pressure, like a water pump, to make the water flow. Electricity is similar. Like the water reservoir, the source of electricity is a battery, generator, or power station. A conductor is a term used for anything that can transport electricity, like a wire, the air, and even the human body. An electric generator provides the pressure to transport electric current in a conductor.
Simply put, a current is the flow of electric charge or electrons. Just as water flows in a pipe, charged particles flow in a conductor. For example, we use the term flow to describe how much water flows through a pipe in a given amount of time. In electrical terms, current describes how many electrons flow through a conductor in a given amount of time. Current is measured in amps. In many ways, but we'll discuss only three more. We mentioned water pressure previously. In electrical terms, voltage is the pressure that drives charged particles to move. Follows the company's electrical safety policies and procedures and instructions of responsible supervisors and the safety and health manager. Brings to the attention of the supervisor and/or health and safety branch potential hazardous situations such as discrepancies between instruction, procedures, policies and manual, faulty equipment, misapplication of the device, etc. Electrical equipment known to be malfunctioning must be repaired or replaced before use. The repair must be initiated as soon as possible after the malfunction is noted. The user is responsible for obtaining necessary tools and safety equipment from the designated storage area, checking it for discrepancies, returning it to storage in good condition, and identifying any faulty equipment to his/her supervisor. Eye protection is required during any electronic or electrical hardware repair, installation, and door open front operation. Electrical safety shoes, long-sleeve non-polyester, low flammability shirts, and insulating gloves will be worn when operating or testing 600 volts or higher equipment.
Protective apron will be worn over polyester or other highly flammable clothing during soldering operations. Make sure all equipment is grounded. Ground fault circuit interrupters, GFCIs, should be used in areas where workers are exposed to wet or humid conditions. Do not touch exposed surface connectors. Never break off the ground prong of a 3-prong plug to allow you to use it in a 2-prong outlet. Any cord with the prong missing should be put out of service. If the ground prong is removed, the piece of equipment is no longer grounded. Whenever you are working on a piece of equipment, lock out and tag the electrical source to that piece of equipment to make sure that it is de-energized. Routinely inspect all cords, plugs, and electrical equipment for damage. Never break off the ground prong of a 3-prong plug to allow you to use it in a 2-prong outlet. Any cord with the prong missing should be put out of service. If the ground prong is removed, the piece of equipment is no longer grounded. Whenever you are working on a piece of equipment, lock out and tag the electrical source to that piece of equipment to make sure that it is de-energized. Routinely inspect all cords, plugs, and electrical equipment for damage. Lockout/tagout is a method of keeping equipment from being set in motion and endangering workers. The OSHA lockout/tagout standard is designed to prevent needless deaths and serious injuries to service and maintenance workers. Before any maintenance is performed on equipment, all sources of electricity shall be locked out and tagged out. Identifying all energy sources to the piece of equipment. Turning off and shutting down all appropriate valves, switches, and circuit breakers. Locking out the piece of equipment by applying a lockable device over the energy isolating mechanism to hold it in the safe or off position. Every worker who will be working on the equipment should attach his personal lock to the isolating device. Applying a tag to the isolation source identifying the work to be done and the person who applied it. After the piece of equipment is locked and tagged out, it should be checked to make sure that energy sources were not missed. Verify the main disconnect switch or circuit breaker can't be moved to the on position. Lockout/tagout equipment should only be removed when the maintenance work is complete, and the equipment has been determined ready for operation by qualified personnel. Except in emergencies, the person who put it on should only do the removal of lockout/tagout devices. Shock. Electric shock occurs when the human body becomes part of a path through which electrons can flow, that is, the circuit. The resulting effect on the body can be either direct or indirect. Direct injury or death can occur whenever an electric current flows through the human body. Currents of less than 30 milliamps, mA, can result in death. Indirect. Although the electric current through the human body may be well below the values required to cause noticeable injury, the human reaction can result in falls from ladders or scaffolds, or movement into operating machinery. Such a reaction can result in serious injury or death. There are 3 basic ways in which shock occurs. A person comes in contact with both wires of an electric circuit. A person comes in contact with a wire from an electric circuit and the ground source. A person comes in contact with a ground source and a metal part that is in contact with a wire from an electric circuit. Burns can result when a person touches electrical wiring or equipment that is improperly used or maintained. Typically, such burn injuries occur on the hands. Arc blasts occur from high amperage currents arcing through the air. This abnormal current flow, arc blast, is initiated by contact between 2 energized points. This contact can be caused by persons who have an accident while working on energized components, or by equipment failure due to fatigue or abuse. Temperatures as high as 35,000 F have been recorded in an arc blast research. Explosions occur when electricity provides a source of ignition for an explosive mixture in the atmosphere. Explosive atmospheres can result from the accumulation of flammable vapors or gases generated by nearby sources and processes. The ignition can be due to overheated conductors or equipment, or normal arcing, sparking, at switch contacts. OSHA standards, the National Electrical Code, and related safety standards have precise requirements for electrical systems and equipment when applied in such areas. Fires. Electricity is one of the most common causes of fire both in the home and workplace. Defective or misused electrical equipment is a major cause, with high-resistance connections being one of the primary sources of ignition. High-resistance connections occur where wires are improperly spliced or connected to other components such as receptacle outlets and switches. This was the primary cause of fires associated with the use of aluminum wire in buildings during the 1960s and 1970s. A GFCI is a fast-acting device that monitors the current flow of a circuit. In the event of leakage of 5 mA or more, the GFCI, in a fraction of a second, shuts off the current to the appliance. GFCIs do not stop shock but limit the duration. GFCIs are commonly used in bathroom and kitchen outlets in homes and generally have a small reset button on the outlet. Electrical hazards, while always present at the company, can be minimized. There are various ways of protecting from electrical hazards. These include locking and tagging equipment, guarding, grounding, mechanical devices, personal protective equipment, safe work practices, safe practices when working with portable equipment, proper use of electrical cords and plugs, safe practice when working at heights. This section describes each of these protective methods. The company has written lockout, tagout programs. The purpose of this program is to isolate sources of electrical energy from equipment undergoing repair or maintenance. Personnel who employ lockout/tagout procedures are given specific training and must be approved to repair and maintain electrical equipment. Live parts of electrical equipment operating at 50 volts or more must be guarded against accidental contact. Guarding of live parts may be accomplished by locating equipment in rooms, vaults, or enclosures accessible only to qualified personnel. Use of permanent, substantial partitions or screens to exclude unqualified persons. Locating equipment on a suitable balcony, gallery, or platform elevated and arranged to exclude unqualified personnel. Elevation of equipment 8 feet or more above the floor. In addition, entrances to rooms and other guarded locations containing exposed live parts must be marked with conspicuous warning signs forbidding unqualified persons to enter. By grounding a tool or electrical system, a low-resistance path to the earth through a ground connection is created. When properly done, this path offers sufficiently low resistance and has sufficient current carrying capacity to prevent the buildup of voltages which may result in a dangerous shock. This does not guarantee that no one will receive a shock, be injured, or killed from grounded equipment. However, it substantially reduces the possibilities of such accidents. OSHA requires that all exposed non-current carrying metal parts of permanently installed equipment which may become energized be grounded when the equipment is within 8 feet vertically and 5 feet horizontally of ground or grounded metal objects and subject to employee contact. Located in a wet or damp location and not isolated. Connected by cord and plug. Mechanical protection devices are designed to shut off the flow of electricity in the event of a ground fault, overload, or short circuit in a wiring system. Fuses, circuit breakers, and ground fault circuit interrupters are 3 examples of mechanical protection devices. Fuses and circuit breakers monitor the amount of current that a circuit will carry. They automatically open or break the circuit when the amount of current flow becomes excessive and therefore unsafe. They automatically open or break the circuit when the amount of current flow becomes excessive and therefore unsafe. Fuses are designed to melt when too much current flows through them. Circuit breakers are designed to trip open the circuit. Fuses and circuit breakers are intended primarily for the protection of conductors and equipment. They prevent overheating of wires and components which might otherwise create hazards to operators. The ground fault circuit interrupter, or GFCI, is designed to shut off electrical power within as little as 1/40th of a second. It works by comparing the amount of current going to an electrical device against the amount of current returning from the device. The GFCI is used in high-risk areas such as wet locations and construction sites. To ensure that a GFCI is operating properly, most GFCIs have a test feature. Test the GFCI regularly. OSHA requires that personnel working on electrical systems be provided with and use electrical protective equipment that is appropriate for the specific parts of the body to be protected for the work performed. The types of electrical safety equipment, protective apparel, and protective tools available are quite varied and include rubber gloves, leather gauntlets, insulating sleeving, insulating blankets, face shields, safety glasses, line hoses, hot sticks, and voltage detectors. Perhaps the single most successful defense against electrical accidents is the continuous exercising of good judgment or common sense. All personnel working at the company should be thoroughly familiar with the safety procedures for their jobs. In general, however, the following safety rules must be followed at the company. Personnel must operate electrical equipment in accordance with the manufacturer's recommendations. The safety instructions and operating procedures for all equipment shall be followed. Employees may not enter spaces containing exposed energized parts unless illumination is provided to enable the employer to perform the work safely. Employees must not reach blindly into areas that may contain energized parts where lack of illumination or an obstruction precludes observation of the work to be performed. Unauthorized personnel shall not occupy areas around electrical switchgear, panel boards, or load centers. When working with electrical equipment, always work with a partner. The partner should observe the work from a safe distance and be trained in first aid/CPR. Where live parts present an electrical contact hazard, employees may not perform housekeeping duties at such close distances to the parts that there is a possibility of contact, unless adequate safeguards, such as insulating equipment or barriers, are provided. Electrically conductive cleaning materials may not be used in proximity to energized parts unless procedures are followed which will prevent electrical contact. Portable electrical equipment is normally classified according to the number of insulation barriers provided between the electrical conductors in the equipment and the user. Equipment that has 2 insulation barriers and does not have exposed metal parts are called double insulated. Double insulated tools provide reliable shock protection without third wire grounding. Conventional electric tools have a single layer of functional insulation and are metal encased. Portable electrical equipment is normally classified according to the number of insulation barriers provided between the electrical conductors in the equipment and the user. Equipment that has 2 insulation barriers and does not have exposed metal parts are called double insulated. Double insulated tools provide reliable shock protection without third wire grounding. Conventional electric tools have a single layer of functional insulation and are metal encased. Double insulation can be provided by encasing the entire tool, or at least the part of the tool which is handled, in a non-conductive material, such as plastic, which is also shatterproof. The National Electric Code permits double insulation on portable tools and appliances. Double insulated tools that have been tested by underwriters' laboratories carry the square-in square-all mark. Equipment with only 2 prongs on the electric plug and without the awl mark is not considered double insulated and is not approved for use at the company. Equipment with only 2 prongs on the electric plug and without the awl mark is not considered double insulated and is not approved for use at the company. Equipment that does not possess a 2-prong plug and a awl mark must have a 3-prong electric plug. The 3rd prong is used to ground exposed metal parts on the equipment. Prior to using portable electrical equipment at the company, the user must first perform a safety inspection. This inspection consists of looking for external defects and for evidence of possible internal damage. If there is a defect or evidence of damage that might expose an employee to injury, the defective or damaged equipment shall be removed from service, and no employee may use it until necessary repairs and tests render the equipment safe for use. The pre-use inspection will include inspection of the tool casing for cracks, dents, contamination, oil, moisture, dirt, corrosion. See electric cords, below, for inspection of cords and plugs. Inspect cords regularly. Look for signs of stretching, insulation damage, and kinking. Don't use if these conditions are evident. Keep cords and cables clean and free from kinks. Kinking can damage both the cord's insulation and internal wire. Never carry a tool by its cord. When using tools that require a 3rd wire ground, use only 3-wire extension cords with 3-pronged, grounding plugs and 3-hole electric outlets. Never cut off the grounding plug from a cord. If you see a cord with the grounding plug missing, have an electrician replace the plug. Pulling on electric cords can damage the cord insulation and cause electric sparks. Always remove the cord at the plug. Pulling on electric cords can damage the cord insulation and cause electric sparks. Always remove the cord at the plug. Extension cords may present a tripping hazard. Make sure that cords are not located in walking paths or a non-trip cover is placed over cords. Always use the correct extension cord for the job. An undersized cord can cause a drop in tool power and overheat. Check the manufacturer's recommendations for the wire gauge, or thickness, and length of the cord based on your application. Portable electric equipment and flexible cords used in highly conductive work locations, such as those inundated with water or other conductive liquids, or in job locations where employees are likely to contact water or conductive liquids, shall be approved for those locations. Hands must be dry when plugging and unplugging flexible cords and cord and plug connected equipment, if energized equipment is involved. Electric plugs and receptacles are designed for different currents and voltages so that only matching plugs and receptacles will fit together, preventing a piece of equipment, a cord, and a power source with different voltage and current requirements to be plugged together. These standard configurations have been established by the National Electric Manufacturers Association, NEMA. In addition to the proper selection of electric plugs, the electric plug must also be inspected properly. Inspection of plugs shall include signs of damaged or chafed insulation, overheating, prong condition, and installation of a ground plug if required. When an unqualified person is working in an elevated position near overhead lines, the location shall be such that the person and the longest conductive object he or she may contact cannot come closer to any unguarded, energized overhead line than the following distances. For voltages to ground 50 kV or below -10 feet. For voltages to ground over 50 kV, 10 feet plus 4 inches for every 10 kV over 50 kV. In addition, portable ladders shall have non-conductive side rails if they are used where the employee or the ladder could contact exposed energized parts. Do you specify compliance with OSHA for all contract electrical work? Are all employees required to report as soon as practicable any obvious hazard to life or property observed in connection with electrical equipment or lines? Are employees instructed to make preliminary inspections and are appropriate tests to determine what conditions exist before starting work on electrical equipment or lines? When electrical equipment or lines are to be serviced, maintained, or adjusted, are necessary switches opened, locked out, and tagged whenever possible? Are portable electrical tools and equipment grounded or of the double insulated type? Are electrical appliances such as vacuum cleaners, polishers, and vending machines grounded? Do extension cords being used have a grounding conductor? Are multiple plug adapters prohibited? Are ground fault circuit interrupters installed on each temporary 15 or 20 amperes, 120 volt AC circuit at locations where construction, demolition, modifications, alterations, or excavations are being performed? Are all temporary circuits protected by suitable disconnecting switches or plug connectors at the junction with permanent wiring? In wet or damp locations, are electrical tools and equipment appropriate for the use or location or otherwise protected? Is the location of electrical power lines and cables, overhead, underground, underflow, another side of walls, determined before digging, drilling or similar work is begun? Are metal measuring tapes, ropes, hand lines, or similar devices with metallic thread woven into the fabric prohibited where they could come in contact with energized parts of equipment or circuit conductors? Is the use of metal ladders prohibited in areas where the ladder or the person using the ladder could come in contact with energized parts of equipment, fixtures, or circuit conductors? Are all disconnecting switches and circuit breakers labeled to indicate their use or equipment served? Are disconnecting means always open before fuses are replaced? Do all interior wiring systems include provisions for grounding metal parts of electrical raceways, equipment, and enclosures? Are all electrical raceways and enclosures securely fastened in place? Are all energized parts of electrical circuits and equipment guarded against accidental contact by approved cabinets or enclosures? Do you have electrical installations in hazardous dust or vapor areas? If so, do they meet the National Electrical Code, NEC, for hazardous locations? Is exposed wiring and cords with frayed or deteriorated insulation repaired or replaced promptly? Are flexible cords and cables free of splices or taps? Are clamps or other securing means provided on flexible cords or cables at plugs, receptacles, tools, equipment, etc., and is the cord jacket securely held in place? Are all cord, cable, and raceway connections intact and secure?